Noise in the copy room, or this is?
Perhaps your attendance has dropped. It is 9 o'clock.
Yeah, but it was 9 o'clock before. So I'm going to, while I can think that it works, maybe show a little demonstration. Let's see, I hope it works. Let's see. I don't know. Oh, round beach ball, maybe it won't. Yeah, okay, well, let's see. Stop. Well, all right, no demonstration for the moment. Hopefully the beach ball will recover. And so we're going to discuss maps, which are like okay. Dynamical systems come in, well, you know, I talked before about there being these binary things. There's incompressible and compressible fluid dynamics. There's dissipative dynamical systems. There's conservative dynamical systems. So there's many ways to draw binary things. And another way to draw a division is between continuous and discrete dynamical system. So you saw, of course, we saw in the first class, a dynamical system wrote as x dot equals f of x, right? So that's continuous time. And discrete time, we're going from, we're stepping in integers here and whole numbers. And discrete time dynamical system is yn plus 1 equals g of yn, where y is a vector. But many of the same tools, many of the same phenomena. We have a fixed point. A fixed point is no longer going to be, you know, the fixed point was f, when we had,
I think it's that. Sorry, Hugh.
that's the thermostat.
Is it that? Oh, that's
No,
thermostat.
that's the thermostat, yes.
Ah.
What are you trying to
I
achieve?
just want to raise this so I can run on the
Oh.
blackboard. I tried yanking at it, but that's not the thing to do. And that's the thermostat.
Yeah, that's true.
And
Is it on the system?
it's on the system. Let's see. But I'm afraid of then eliminating that, so maybe I shouldn't.
It'll probably be on there.
Advanced controls, it would be on here, you think?
It's me.
No, that's not what I want.
Yeah, people have been foxed by this before.
See, I went to advanced controls, which was the only thing I could,
Yeah.
and that tells me
Yeah.
more audio visual stuff.
it is.
No, it doesn't matter. Well,
No.
see, I believe that it seems to only.
Oh, right screen.
Oh. And where was that?
Under lighting.
Lighting?
Lightning.
It was under lighting.
All right, okay.
Right.
Okay, anyway, I was just going to say something very simple. A fixed point, of course, if you write x dot equals f of x, a fixed point is going to satisfy 0 equals f of x bar, right? Whereas if you write y of n plus 1 equals g of yn, then a fixed point is such that g of y bar equals y bar. So it's not 0 that you're looking for g's, it's fixed points, right? I mean, that's pretty obvious. And so we, as before, we look for the fixed points, we look for the linear stability. And the fixed point, of course, is something that satisfies that when G acts on it, it doesn't change. And then we set Y to be the fixed point plus a perturbation, epsilon, and we look at the evolution of perturbation. And so Y bar plus epsilon n plus 1, that's Y n plus 1 here, is equal to G of Y bar plus epsilon n. Just as before, we expand in the Taylor series, G of Y bar plus G prime of Y bar epsilon n plus 1/2 G double prime of Y bar epsilon n squared. Now, instead of having G of Y bar being 0, we have G of Y bar is Y bar, right? But as the equation turns into the same thing, epsilon n plus 1 is G prime of Y bar epsilon n. We've neglected the quadratic terms. That's what linear stability is. Before, okay, again, now this is a difference equation. Before we had the differential equation. Let's write it in a different way here. Say, before we had, right, and then for the perturbations, we had epsilon dot equals f of x prime epsilon, and so we had epsilon of t equals e to the f prime x bar of epsilon 0, and I'd made a mistake there, and someone corrected me. I don't know if he's still here. Right here we have yn plus 1 equals g of yn. Fixed point is g of y bar equals y bar. We get epsilon n plus 1 equals g prime of y bar epsilon n. The solution to this is not an exponential. The solution to this is epsilon n equals g prime of y bar to the n epsilon naught. Everybody agree with that? Yeah. Each time you multiply by g prime of y bar. So here you had stability. The question was, is f prime of x bar greater or less than 0? Because that's when you'd have growth or decay. And here again, you're interested in growth or decay, but that's obtained if g prime of y bar is greater than 1 or less than 1 in absolute value. Growth or decay. Okay, everybody agree with that? Now we're concerned with what its relationship is with 1 in absolute value, whereas before we were concerned with the sign. Yes?
Actually,
Did I make a mistake? It's
just
your
another question.
your chance to make
I have a
correct
question.
me then.
I just thinking it should be epsilon. Is you are referring to n delta t, right?
There's no delta t here.
But
There's no. Do you see a delta t? I don't see a delta t.
because I'm just thinking that when you take the power of n, so you are multiplying n at every time step, right?
That's right, exactly. And if the thing that you're multiplying is greater than 1, then the thing gets bigger and bigger. And if the thing you're multiplying by is less than 1 in absolute value, then it gets smaller and smaller.
Just think that I don't know why you write it as epsilon n. I don't know if this is the correct way to write it.
Oh, because again, remember the first day I made a big mistake, so it's possible that I'm not understanding what you're saying. But look, here's the epsilon. The epsilon is the deviation from y bar. Just as before, here we would write, this was x of t equals x bar plus epsilon of t. And here this is g, excuse me, no, not g. This is yn equals y bar plus epsilon n. Okay, but as I say, I just last week I made exactly mistake in writing exactly this. So are you sure you're not satisfied yet? Tell me more.
No, that's fine.
Wait, look here then. Here we wrote, this is yn plus 1, which we've written this way, that we can always do. That's a definition of epsilon n plus 1. And then I substituted in here for yn, y bar plus epsilon n, in the Taylor series. Okay, and then this and this canceled, and this we neglect. Yes?
n and n plus 1 represent the nth time step and n plus 1th time step, right?
Well, you can call it
A
a time
sequence.
step if you want.
Okay.
Uh,
It's for any general variable in a sequence.
That's right, yes. That's what I prefer. In particular, okay, a very non-time step-ish way of looking at it is in ecology, where there's a population of one generation and the next generation, that's kind of intrinsically discrete, number of rabbits or something that depends on the number of rabbits before, and there isn't a delta t that you can take smaller and smaller. I mean, you could formulate another theory of with ecology that would have delta t smaller and smaller, but the discrete time version looks like that, and it's one generation to the next. Okay, there's one more definition here which doesn't exist for the continuous one. You can see that the case of g prime y bar equals 0, that is, okay, it gets smaller and smaller when g prime of y bar is less than 1, okay? But when g prime of y bar is 0, you can see it gets smashed down, and that's called superstability. Right? Here it's going down like a polynomial, like a power, but it's excuse me, if you're stable, you're going down like a power, but if you are, if g prime of y bar is 0, then you're going down faster than a power. There. So that is to say, this is always true if you neglect, if you do asymptotics and you neglect higher order terms, and then you find that what's left is 0, well then you should start with the higher order term, and you get this, and you get quadratic growth rather than, or decay rather than linear. In fact, that's what's behind the success of Newton's method. Okay, so now, from before, okay, we're going through the same thing that we did for the first class in dynamical systems, but for the discrete ones. When we lose stability, okay, there'll be bifurcations when you have a transition between g prime of y bar equal 1 in absolute value and not equal 1. So they're crossing, but now we're looking in absolute value as they cross. Before we were just looking at a sign change, greater than 0, less than 0. Now we're looking for a change in absolute value of g, and there are 3 ways that that g prime could cross if you had a multidimensional system. If you had a multidimensional system, then you would have eigenvalues of a matrix, as we discussed before, and then those could be complex conjugate. Even in the one-dimensional way, you don't have complex eigenvalues, and then you have only 2 possibilities. It could cross by 1 and cross by -1. And each of those is going to give rise to a new kind of bifurcation. Now let's let's look at the 2 cases that we just mentioned here, the one-dimensional cases exiting by +1, exiting by -1. What I've drawn here, these are called cobweb diagrams, and some of you may have seen them in previous schooling maybe. It's a way of iterating a map. I mean, of course we could write we have a y0, and then we have g of y0 for y1, and then we have y2 is g of y0. But there's a simple, and so on, but there's a simple graphical way to do this. That's what the cobweb diagrams do. Here is drawn, now I tried originally when I made these slides to have every place for the continuous dynamical systems an x and an f of x, and then for the discrete ones a y and a g of y, but very quickly I was making mistakes and going back to x and f of x. So here, this x and this f of x, these are discrete dynamical systems, even though it's not written with y and g of y. Okay. The diagonal is written in red, and the function is written in black. And here's my initial condition, x naught. So f of x naught is my function, which is in black. That's x1. But that's in the vertical axis. I want to put it on the horizontal axis. And how do I put the value that's here? I want this value here that's on the vertical axis, but I want it on the horizontal axis. Well, what you do is you go over to the diagonal and then come down, and that's the x1. this value here, x1, is the vertical value f of x naught. Okay? I mean, it's, you can see it's on the diagonal, so so its y value is, its vertical value is the same as its horizontal value, right? And you certainly know that its vertical value is f of x naught, and hence, and since it's on the diagonal, its horizontal value is also f of x naught, right? Okay. So this is what you do to iterate. You go to f of x here, and now you go across, and you don't even really have to go down to the axis. What you have to do is go back to the function to get f of x1, and then across, and then f of x2, and then across, and so on. Okay? And you see now that you are converging to this point, and what is this point? It's the intersection of the function f of x and the diagonal, naturally enough, since fixed points are on the diagonal, right? They're points such that the function, which is black here, has the same x and y values, and that's the case when it intersects the diagonal. So here, this is an approach. X bar is a fixed point here, and this is an approach from x naught to x bar. Now, and this is the simplest thing, it's a linear function, just a line with a different slope. Now let's take a linear function with a higher slope here, 1.5x, and again, the red is the diagonal. Let me start at x naught over here. My fixed point is x bar, where the two intersect here. I start with x naught. I go to my function, which is the black line. I go across to the diagonal. I go vertically to the function. I go horizontally to the diagonal, vertically, horizontally, vertically, horizontally. And you see that what I'm doing is I'm leaving the fixed point. I'm not approaching it, I'm leaving it. And indeed, this should not be unexpected. We just saw that the question was whether that derivative was greater or less than 1. Naturally, a function with 0.5 times x has a derivative which is a half, so that's a stable fixed point. And this one has a derivative which is 1.5, greater than 1, and hence it's unstable. Okay, everybody agree with that? Okay, so we've seen an illustration of stable and unstable fixed points. Now, let us look at the exit by -1. There's two ways that you can, if you're a scalar, there are two ways you can exceed one absolute value. One is being 1.5, and the other is being minus 1.5. We do the same thing. We have a function minus 0.5x. The fixed point should be stable. Fixed point is the intersection of the diagonal with the function here. We start off with x naught. We go to the function, which is the black line, vertically. Then we go across to the diagonal, then we go vertically to the black line, the function that gives us x1, and then x2 is gotten, excuse me, is actually, yeah, this is x1, but that now, yeah, this is the value x1. Now we're going to, we need to put that on the, excuse me, we take f of x1, and that's here, and to get it on, that's here, vertically, and to get it onto the horizontal, we put it here, so that gives us x2. We go vertically to the black line, horizontally the red line, and so on. And we see that we're going towards the fixed point x bar. But we see that we're doing it in an oscillatory manner, and that goes along with the fact that there's minus here. We're changing sign. Here, the epsilon is, indeed, it's decreasing in absolute value, but it is changing signs each time. This g prime is negative, and so you're multiplying by minus 1/2 each time. So you're here, now you're at a smaller distance, a half of it, but to the left, and now you're at a distance 1/4, but to the right, and now you're at a distance 1/8, but to the left, and so on. And that's what's happening here. Now here's f of x equals minus 1.5x, and so that's going to be unstable, and it's going to be also oscillatory because of the minus sign. So here's our fixed point, the intersection of the black line with the red line. We go to the, excuse me, we are a little bit to the left of the fixed point here. We go to the black line to get our function value. We go to the red line to put that on the horizontal axis. We go to the black line to get a new function value. Again to the horizontal axis we go, and we see that we're going left, right, but we're spiraling out in this picture. That's not the same as a spiral that we have in the dynamics, in the continuous two-dimensional dynamical system. Okay, this is going right, left, right, left, right, left. And this is an important fact about discrete dynamical systems. I'm saying we can go right, left like that, but notice we're not going to the in-between values. We could hardly go right, left, right, left. If this was a continuous system, we would be crossing 0 each time, and then there would be a change in, do you go right, do you go left? Here, the values that exist in this sequence are to the right, to the left, to the right, to the left, to the right, to the left. They're not on 0. Hence my emphasis about it being a discrete one. There's not delta t here. There's not a sense in which, okay, otherwise you couldn't go from right to left like that. This is an important phenomenon that does not exist. We'll talk about it shortly. There's something called period doubling bifurcation, which many of you have probably heard of, that does not exist in a continuous system for precisely this reason, because you can't go from positive to negative without passing through 0 if time is continuous. Okay, so this is just parallel to the other class. Let's say we did fixed points, we did stability, and okay, we're finished with stability. This really says everything about stability pretty much, in 1D anyway, and almost all in 2D. But now we want to see something more complicated. We want to see how change of stability takes place. I mean, here we would say this function it has one fixed point and it's always stable. So that's the end of the story, and it's a kind of boring story. This one has a single fixed point and it's always unstable, and that's the end of the story. We want to have a story to tell, and so we go to nonlinear functions where we change the number of fixed points and we change their stability. I recall that the word bifurcation means change in number of solutions or their stability. Okay. As before, the simplest one is the saddle node bifurcation. You recall that from last week. We had that normal form, x dot equals mu minus x squared. When mu crossed 0, we went from having no solutions to 2 solutions, one of which was stable, one of which was unstable. Okay. The simplest way to study discrete dynamical systems is to change the x dot to a finite difference, xn plus 1 minus xn. And so here we will have a new normal form, xn plus 1 equals xn plus mu minus xn squared. And the derivative of that is 1 minus 2xn. When we look for fixed points, well, you can see we're looking for does this leave x unchanged? Well, that's obviously when mu minus x squared is 0, then xn plus 1 would be xn if mu minus xn squared were 0. So we're again interested in the positive and negative square root of mu as before. And now let's use the same kind of picture as over here. Let's write that function that's on the right-hand side, and let's see how it evolves as mu changes. For mu negative, the function, this quadratic function, does not intersect the diagonal. This is mu minus xn squared. It does not intersect the diagonal. And for mu positive, it intersects the diagonal in 2 places. It's very much like what we did with the continuous ones. The 2 places are plus or minus square root of mu. And if you take the derivative of that, you get 1 minus 2 square root of mu. And remember, square root of mu is positive for these fixed points to exist. And 1 minus 2 square root of mu is negative. And so that is stable. And, plus square root of mu is 1 minus square root of mu. So that's less than 1, right? So that's stable. And the other one, the one with the minus sign here, the lower one, minus, is 1 minus 2 square root of mu. So that's 1 plus 2 square root of mu. That's positive, and that's unstable. And so that's what's written here with the dot open and closed dots. And then here we make a bifurcation diagram as a function of mu. We have stable and unstable fixed points here. And here we draw the arrows that show that it's stable and unstable, with the difference, again, that this is, here it's much more schematic because we have a discrete dynamical system and we're not just going down this arrow continuously, we're jumping. But still, the basic idea here is the same. And we have pitchfork bifurcations. What are pitchfork bifurcations? Well, you recall we had x dot equals mu x minus x cubed. Now, let's just change the x dot to xn plus 1 minus xn, and that will give us the function xn plus mu xn minus xn cubed. So that's a lot like before. We take the derivative, and it's 1 plus mu minus 3x squared. So fixed points of this, xn plus 1 is xn when xn squared is, when either x is 0 or x is plus or minus square root of mu, just as before. Okay. X can't be plus or minus square root of mu and be real if mu is negative. So for mu negative, we only have x equals 0 as a fixed point. And this is what the function x plus mu x minus x cubed looks like. And this is the intersection with the diagonal. So here's a fixed point. And if we look at the derivative of f prime of 0, it is 1 plus mu. And for mu negative, this is less than 1. So this is a stable fixed point. And note what we're saying about it, maybe I didn't emphasize this enough. The slope here is less than 1. That's what makes it stable. The slope being less than 1 is what led to the fact that this went in here. Here also the slope was negative, but less than 1 in absolute value, and that's what led to this curling in here. Whereas when the slope is greater than 1, when it's compared to the diagonal, you can see it's easily that it's greater than 1. That's when you leave. Okay. Now, if you take this function here and you push like that, which is what you're doing by adding some mu x, you push down here. Push this down, push this up, while keeping this cemented here. And you keep this cemented here, that's because of the absence of a constant term, because the x remains throughout. So you always, x equals 0 remains a root. It stays anchored on this. And when you push like this, and you see that you change the slope from being less than 1 to greater than 1, and you create two new fixed points, which are stable at onset. So we get the same pictures as we did for the continuous system. And as before, the pitchfork bifurcations come in two varieties, supercritical and subcritical. You remember this picture where on one side you have a stable fixed point surrounded by, and on the other side you have an unstable one surrounded by two stable ones. Subcritical is the other way around. You have a stable one surrounded by two unstable ones, and here you're unstable everywhere. And that's what that function looks like. You can see it's a very fundamentally unstable situation. The slope is greater than 1, and here, if you get x larger, there's a small interval where you converge here, and everywhere else you leave.